Welcome to today's lecture and the last module of the lecture series on fluid inclusions in minerals. We have browsed through, or we have kind of got an overview of fluid inclusions, their different types, the diversity in the host minerals, in diverse type of geological environments, and now we will discuss something that we have planned to, that the need or the use of computer programs and softwares for the analysis of the fluid inclusion data, the raw microthermometric data that we acquire from our heating freezing experiments, and how to present or their presentation of the data in different forms, as we have seen before, like histograms, bivariate plots, and the isocores, and the procedure calculation procedure involved in calculating the density of fluids. Sometimes they are the mixtures of water with other gaseous species. The discussion in this particular module will be more general rather than any rigorous involving any rigorous formulation and mathematics, or even not going into any of the fundamentals of computer programming as such. But the thing is that actually when we say computer modeling, it is not that very appropriate to the use of computer programs or software in fluid inclusion work, because it involves only the calculation of certain parameters from the raw microthermometric data, and most of the time, most of the cases, it boils down to something like formula translation. Because during the course of our discussion, we mentioned, we saw the formulations, different types of empirical equations, of which we call them as the equation of states. They were developed for the calculation of the volumetric properties of inclusion fluids at different temperature conditions, different for aqueous inclusions or aqueous carbonic inclusions, the salinity of the aqueous phase and the density of the carbonic component, and then when they homogenize to a total homogenization, how to calculate their density and isochore. So, these formulations have actually been developed by rigorous procedures of theory as well as empirical observations, and sometimes like the discussion which we made on the modified Redlich-Kwong type of equations, they were essentially can be called as semi-empirical in nature, by considering certain theoretical aspects of interaction of molecules at different pressure and temperature conditions, plus what exactly has come from observations or the experimental measurements of volumetric properties, and then through some analysis like regression type of analysis or different types of mathematical techniques which are used to finally formulate such equations, which will be directly usable for volumetric properties calculation for fluid inclusion, whatever we get from the microthermometry. So, the first point that the need for a computer programmer software comes when, because these days, because if we take the simple example of when we saw the, for example, a weight percent NaCl equivalent from freezing point depression data, we say okay, simply that weight percent of NaCl is just equal to some parameter A0 plus A1 into theta, which is the depression of the freezing point from 0, plus maybe A2 theta square. So, when this is a very simple equation to calculate the salinity of an aqueous inclusion where the freezing point depression data is available. Now, the thing is that we measure the inclusions in large numbers, and calculating them by hand will be time consuming and error prone. But then these days it is very simple. Even if we use kind of an Excel, Microsoft Excel worksheet, there also we can for any particular field which we call as a cell, we can write the formula, and this formula will be a very simple formula to put, so that when on one column when we give our salinity data, sorry, the depression in freezing point data theta, and for this particular column we just put the formula bar that it will just convert this depression and freezing point to salinity, then just with a click of mouse we will get the data for salinity. And but then when it comes to a situation where we have to calculate the density of an aqueous fluid from temperature of homogenization and salinity, there it is a 10, 12 or 14 coefficient nonlinear regression equation, and that will be possibly not that very easy to put in an Excel sheet and do this thing very easily. So, in that case there is a need that we write a computer program and then run the program and give the input values as our temperature of homogenization and salinity, and then get the density values, and also the formula that we have seen for calculation of the dp/dt slope, which is a function of salinity and the temperature of homogenization and salinity, we can also calculate the slope. So, the need for a computer program arises because of the length of the calculation, the rigor of the calculation procedure involved, and the amount of microthermometric data, the quantity of the microthermometric data that we have generated, which may be in hundreds of thousands. So, then there was a need, and in the older days when there were no much of facilities were available, like what I am talking about, the Microsoft Excel also is a development which came much later compared to when in the 70s or 80s, when such kind of a fluid inclusionist needed to analyze his data or process his data in the form of the final presentable form. So, the need was very much there to. So, there were many people. So, in the early stages there were many workers of fluid inclusions who were writing small Fortran or the small programs in high level programming languages like BASIC or Fortran. If someone looks at the the journal which actually publishes computer the Computer and Geosciences journal, which is published from Elsevier, if someone browses the content of this particular journal, the old archives, one will see a lot many such small, such Fortran or BASIC programs which were used to get published by various authors at different points of time. I am not giving an exhaustive list of them, it is essentially not very relevant here, but the only problem was that when there was a code in a high level programming language like BASIC or Fortran was written or given by somebody, then one need to have a platform like a compiler and where he will run the program, execute the program and get the results, which was also not that very easy in the earlier days. Then what actually happened, the later development, so it was much easier. So, those kind of programs which were written in high level programming languages like Fortran or BASIC, those programs were essentially what one can say that they were these days when this computer is available to anybody and everybody, and these the operating system, the Windows operating system that we use, and there so much the graphical user interface based that we simply just click of the mouse on the button, we get many of the jobs done, like menu bars, dialog boxes, windows, all these kind of things have become so very user friendly these days, which was not there previously. So, most of these programs which used to be written in high level programming languages like when I am talking about, they were based on non graphical user interface based, because one has to get the give the input in terms of either from the console or from in the form of a file, and then also get the output in the form of number. And then there was a need that whatever data we get, because if for a fluid inclusionist to present his data, to look at the statistics of either a salinity distribution or a temperature, density, etc., we need to first plot them on a histogram to look at the fluid characteristic or assess the fluid characteristics, or we need to plot them on the fluid evolution diagram, which were our paired TH salinity diagrams, or and then the isocores. So, there was whatever used to come as a output from these kind of programs, they have also again to be taken to a whatever graphics utility programs are available, they have to be taken there and do the plotting. So, it was always necessary that graphical user interface based program be developed, and with Windows, Microsoft Windows coming into the as a main operating system for the desktop computers, personal computers, it became easy, and also it gave people the scope for development of graphical user interface based program. So, in that situation I will discuss a little bit about them later. And so, sensu stricto, if we so then the later development were all on based on the right developing computer software which would run on, which will be essentially graphical user interface based and to run on Windows type of environment, which will become much user friendly for users to use. And then we will look at the current scenario and discuss what is actually available. So, this discussion will be more general, and whereas the assignments for this particular module will be based on some hands on calculation exercise which will be given to you in the course of this lecture. Now, if we talk about modeling, so actually, so where modeling is essential or useful, in case of fluid inclusion data analysis and presentation, as I said that it just needs to be something like formula translation, whatever available formulations are there, they need to be put in the form of computer code, either on a non graphical or a graphical user interface as you will see them, and can do the job. But the modeling exercise, the computer modeling or the modeling exercise, what actually we mean, they are more useful for quantification of the fluid rock interaction. In fact, most of the study of the phase equilibria on the fluid mixtures, whether it is only water plus electrolyte or water plus gaseous volatile species like carbon dioxide, methane, and the electrolytes, the basic idea of development of this PV Tx relationship is essentially targeted towards quantification of this fluid rock interaction process, because the fluid rock interaction process that is taking place, if we write any whether this is on a surface process or any subsurface or deeper earth processes, it is essentially an interaction of fluid rock, whether it is ore forming environment or metamorphism of different grades that is taking place in the subsurface. So, these interactions whenever it involves a fluid phase. So, the fluid phase means it is a fluid mixture. So, any reaction that someone writes involving minerals, and if it happens to involve a fluid phase, then it is always necessary to compute the fugacity coefficients of the component species in a mixture. Say for example, we have a mixture of CO2 plus H2O. Let us say simple system like CO2 H2O. If it is a mixture of CO2 H2O, then we need to compute the fugacity coefficient of carbon dioxide and water independently, so that we could calculate any reaction equilibria which involves a fluid phase, and that fluid phase is not a pure fluid phase, but a mixture. So, now the situation is that in case of this fluids like the one which we are talking about, the component, the fugacity coefficient of this component, this each component species, if I put it as kind of gamma I. So, I standing for the species like carbon dioxide or water. This is a very intricate function of the PVTX relationship of this particular fluid. So, this fugacity coefficient term in order to be computed can only come from the PVTX. Once the PVTX relationship is established, then only it will be possible through standard formulations and through use of thermodynamics to calculate the fugacity coefficient, which is an important parameter for quantification of any fluid rock interaction process where there is a fluid phase involved. And that, so once this PVTX relationship which is formulated, it is also is useful for volumetric property, for the calculation of the volumetric property of the fluid inclusions. So, since fluid inclusions is being used as a tool, so fluid inclusion and fluid rock interaction and the formalisms that we are using in a fluid rock interaction, they are very much related to each other. So, it is always, we can get a clear picture only when we see them together, but we do not have much of scope of discussing much of the rigorous exercise involving the calculation of the fugacity coefficient of gaseous species. But then the use of actually a computer modeling is essential whenever we are doing some or development of any of the existing formulations. Say for example, if we have our situation is that we suppose we are talking about a only an aqueous fluid. So, that aqueous fluid is water plus electrolytes. These electrolytes are our mainly the chlorides or any other anionic species. So, here also when we talk about the PVTX relationship, this PVTX relationship is also coming into picture. For example, we want to when we quantify a fluid rock interaction process involving a aqueous phase which is a fluid. So, there we also know that the way we can express the total free energy which is a which is contributed by the components from the, it's a solution, and as we deal with crystalline solution, we also can look at this aqueous solution in the much the same way, but in a different type of formalism or different logics is applied to that. Will come from a mechanical mixture component, it will come then from a ideal contribution and non-ideal contribution. So, we are mostly, so as far as the modeling part is concerned, it is always to account for the non-ideality and the parameters that would be contributing to the non-ideal behavior of this particular fluid mixture. It is a particular fluid, and this non-ideality in case of an aqueous electrolyte would be depending on there are lots of long range and short range interaction parameters of these aqueous charged as well as the aqueous neutral species that are present at different pressure and temperature conditions. So, the computer modeling actually is applied to whenever we are looking at them and then trying to improve upon the activity composition relationships in such kind of fluid mixtures, and with an ultimate objective of applying it to fluid rock interaction processes in a better way to better quantify, and also at the same time a refined PVTX relationship in this kind of situation is also helping us to more accurately calculate the volumetric property like the density and the isochore. As I told you that even the at this particular point of time, even systems, very simple systems like water NaCl system, it's still being revisited. For its more rigorous analysis of the phase relations and the immiscibility region, or whether at all there is an immiscibility in this particular fluid, and even till today also this particular system is being revisited, and also systems like H2O, NaCl, CO2, it is still one of the most widely studied system, but as yet a full a completely a formulation which will be accurately applicable to all pressure temperature conditions pertaining to many types of diverse type of art processes is yet to emerge for this particular system, because it has been a difficult system and experimental data for this particular system has not that been much. To give you just an example what I discussed, that the fluid rock, the computer modeling is used in actually working out the PVTX relationships. From that in turn the non-ideal parameter in the fluid mixtures to be quantified, and the suppose for example this I am showing it just to demonstrate that suppose there is a reaction dolomite plus talc giving rise to tremolite, forsterite, carbon dioxide and water. So, you could see that it is a fluid mixture that is associated with this particular reaction. So, this reaction topology, this reaction boundary will very much depend on what is the composition of the fluid in terms of mole fraction of carbon dioxide and water, and not only that, the reaction boundary will very much depend on the accurate calculation of the fugacity coefficient of both this water and carbon dioxide, and which needs to have a very concrete formulation on the PVTX relationships, and that is how it is related. So, and that is the part where a rigorous computer modeling involving the analysis of the experimental data or some theoretical considerations, and then such kind of quantification will be more possible. And here just to show that if this is showing as a pure carbon dioxide system fluid where the pure carbon dioxide and water, here the carbon dioxide and water is charged with a little bit of sodium chloride. This one is 0.0715 mole fraction, which gives rise to an immiscible region, and because of that immiscible region the topology of the reaction boundaries and the invariant points are also changing. So, this is just for the sake of example, not just to make you feel that what exactly when the computer modeling is so many of the programs that we are seeing, for example in I will just briefly go through some of the things that later development in the computer program or software for fluid inclusion data, and okay. So, when just about the time when this non graphical user interface computer codes were getting published for use of fluid inclusion is to process their data and for volumetric calculations for density and isocore. Right about the same time with Microsoft Windows coming, this particular package, the Flynn Core, was published in about 1989 by Phil Brown from University of Wisconsin. There was a very popular software package that was there at the time for fluid inclusions. Almost everybody was using this particular software package. I am just giving an example because these days it is not actually compatible with the later versions of the Windows operating system, but this gives some insight, some idea as to how the packages could be developed, or how it was developed, what was the form of the utility. So, this package was actually for mainly targeted for isocore calculation. So, that is why it was named as Flynn Core. So, fluid inclusion isocore, and this was like working under a graphical user interface where there could be windows, there are dialog boxes, where editable boxes where they could appear, and people could give their input data and get the calculations done. Just for example, it is a case in which an H2NaCl one chooses a system that his inclusion belongs to. So, when the microthermometry data acquisition is over, the user has to specify that what system that particular inclusion fluid belongs to, gives the choice, and then he was given a drop down menu with choices from many formulations that was available at that time to choose one of them, and then open an input box where it could give either freezing point depression or halide dissolution temperature or molality or weight percent NaCl or mole fraction. So, these parameters need to be even calculated. One may not be having readily available. So, it is as it is shown that suppose a -10 freezing point depression is given, and the homogenization of temperature was given, also specified in a different box, and on clicking the calculate button, one gets data on the for the particular inclusion. The salinity, the density data are calculated and displayed along with the isocores which were calculated from a particular temperature range. So, those formulations, they were actually formula translation from the existing formulations at that time. Suppose a particular formulation was only applicable in a range of 300 to 700 degrees Celsius, then the warning is to come, okay, this isocore should not be calculated above 700 degrees centigrade or 3000 bars, depending on the formulation of the proposed by the authors, like for example what is written here. So, the limitation was that, so it did not have any, so only at one particular time only one inclusion data could be processed, and what was coming as a display as the isocore for the pressure at any corresponding temperature interval is because they were distributed in the executable code. So, whatever interval 300 to 700 degrees Celsius with 100 degrees Celsius interval was kind of by default, and this data has to be taken and exported to some other kind of graphing software to plot the isocore. Similarly, the examples are like this is for pure CO2, and similarly whatever was the formulations available at that time for CO2 was to be chosen by the user, and the calculations will be displayed, and the isocores used to get displayed. So, this is what is the many systems that are available at the time, like for methane, for a fluid mixture like carbon dioxide, methane, hydrogen, H2S, CO, H2O, N2, SO2, and there were some formulations which are available which could calculate the PVTX relationship in such kind of a complex fluid mixture, and the isocores to be displayed, and again that has to be copied down and then taken to a particular any other particular software where the graph could be plotted. So, it was not this is an example of a pure nitrogen. Here this only the warning message one could read that it has temperature of homogenization should be between -147 to -208 degrees Celsius, and it was for H2NaCl and KCl, the kind of formulations which you also discussed. So, now this was again this limitation notwithstanding, these programs were written in C programming language and were distributed, and the only situation was that those softwares were available, they were to be procured and to be used. So, wherever people were not able to procure that software or use it with their machines, they used to depend on writing their own programs, again in the same way, formula translation, and then process their data. So, we will continue discussing on this in the next class. Thank you.